Okay, so we'll begin today's lecture, the second method. The first method was the superposition method to deal with the indeterminate structures. The second method will be three-moment equation method. Okay, let's discuss the steps of the new method in a small example. The same requirements, draw shear force diagram and bending moment diagram, but using the three-moment equation method. Okay, forget about the degree of indeterminacy and the steps of the superposition. They will not have the same steps. The first step here, please calculate the moment at each support. Please calculate the moment at each support. So how many supports do I have? I have three supports. The first support at A, and I have another support at B, and a third support at C. What's the moment at A? I can calculate the moment at A from the left, right? So it's 2 times 1.5, so it's 3 ton-meter. I need to know the sign. Is it negative 3 ton-meter or positive 3 ton-meter? It depends on clockwise or anti-clockwise. It's like this. 2 times 1.5, it rotates like in this direction anti-clockwise. So the tail is above, so it's negative 3 ton-meter. Negative 3 ton-meter. What about the moment at support B? Can I know the moment at support B? If I decided to calculate it from the right, I have a reaction here, YC. I don't know the reaction. And if I decided to calculate it from the left-hand side, I also have a reaction here, which is YA, it's unknown. So I can't calculate the moment at support B. So it's unknown, right? What about the moment at the third support C? Yeah, MC, it's very easy. From the right, nothing from the right, so the moment equals to 0. So here, I call this kind of examples, it's ones, not like the ones in the superposition. Once in the superposition, it was the degree of indeterminacy is 1, so it's redundant minus equation. So that means once in the superposition means that I have one extra redundant. But here in the three-moment equation, I am dealing with the moments at the supports. So here I have one support only that I don't know the moment at it, okay? So here I have only one redundant, okay? So this will be the first step. Please calculate the moment at each support, okay? What will be the second step? The second step, split each span individually. What is the meaning of the span? Span is the distance between two supports. So I have here span BC and span AB. Just take care from the part AD. In structure analysis 2, I'm dealing always with indeterminate structures, right? And structure analysis 1, I was dealing with determinate structures. What about the part AD? Is it determinate or indeterminate? It's determinate, right? I can draw shear for part AD. I can draw the shear. I will, when I draw the shear, I have two and then horizontal, and then I can go out. What about the moment for part AD? I know the moment for part AD. The moment at A is negative 3, and here the moment is 0. So the part AD, I call it a determinate part. When you find a determinate part in your example, you have to get it away. But before you get it away, you have to take its effect. What was the effect of the part AD? That the moment at A is negative 3. But when dealing with the extra remaining steps for the three-moment equation, I'm not seeing this part. AV is not here. I just throw it away, but before I throw it away, I have to take its effect first. Okay? So now I have only two spans. Span from A to B, which is simple beam, and span from B to C, which is also simple beam. If the support at C was fixed support, also in the second step, when you split each span, it has to be simple beam. The equation, the three-moment equation, it has a proof. The proof is based on that each span has to be a simple beam. So even there is a fixed support, each span has to be a simple beam. Okay? And put the loads of each span. So here I have a uniform distributed load, 1 ton per meter, and here I have a concentrated load for. So this is the second step. What will be the third step? Draw bending moment diagram for each span. Can I do the bending moment diagram for each span? Yeah, it's easy. Here 0 and 0, and then PL squared over 8, right? So it's 1 times 6 squared over 8, which is 4.5, I think. 4.5. What about the moment? Can you draw a moment here? Yeah, it's easy. Either you calculate the reaction here, which will be 2 and 2, and then the moment here will be 2 times 3, 6. Or you know that this is P times L over 4. You took this in structure 1. For the uniform distributed load, it's PL squared alpha over 8. And for the concentrated load in the middle, this is a concentrated load in the middle, so it's P times L over 4, which is 4 times P is 4, L is 6 over 4, which is 6. The same if you calculated the reaction here, 2 and 2, and then you calculated the moment 2 times 3, 6. So the third step will be draw moment plus conjugate beam. Oh, again conjugate beam, yeah. Again conjugate beam. So you just told us that each span will be simple beam. So that means that the conjugate beam will always be simple beam. Yeah, the conjugate beam here will always be a simple beam. So can you calculate the new reactions of the conjugate beam? This is the fourth step. Can you calculate the new reaction? So I have first to bring the areas, calculate the areas of the moment. What's the area of this curve? It's 2 over 3, base 6 times height 4.5, divided by inertial coefficient, which is 2. Okay? So I think it will be 9. So what will be this reaction? 9 in the middle, so this will be 4.5, and this will be 4.5. The same on the other span BC. Let's calculate the area of the triangle. Half. Base is 3 times height is 6, divided by inertia factor is 1. So this will be 9, and this will be 9 as well. So the reaction here will be 9, and the other side will be 9. These reactions are called elastic reactions. Elastic reactions. It's on the deflection mechanics of structures. Okay. Elastic reaction. What are the elastic reactions? The reactions of the conjugate beam. The reactions of the conjugate beam is called elastic reactions. And then you have to apply the three-moment equation. Where will I apply the three-moment equation? You will apply the three-moment equation at the support that you don't know the moment at. So I have only one support that I don't know the moment at it. So the three-moment equation, we will apply it at what is the equation? The equation will be 2, the moment that I am applying at, so it's 2mb. Open bracket. What is the span before? What is the span? It's 6 meters, right? So 6 divided by the inertia factor, which is 2, plus the span after. What's the span after B? It's BC, which is also 6 meters, divided by the inertia factor, which is 1. And then plus and plus. So I begin the equation from the middle part. The left part will be, what is the support on the left of B? It's MA. What is the support right of B? It's MC. And you will bring this term here, 6 over 2. And you will bring this term there, 6 over 1. Equals. So all of this is only the left-hand side of the equation. The left-hand side of the equation. What's the right-hand side of the equation? It's negative 6 times RB. What's R? R is the elastic reaction. What's the elastic reaction at B? It's 4.5 from this part and 9 from the other part. So RB will be equal to 13.5. 9 plus 4.5. Okay. Moment at A is negative 3. Moment at C is 0. And RB is 13.5. So from this equation, I can calculate the MB. MB will be equal to, I think, negative 4. Negative 4. Can you draw the bending moment diagram now? Can we draw the bending moment diagram? You will ask me, okay, how can I draw the bending moment diagram? I still don't know the reactions. I need YA, YB, and YC. No, I can't draw the bending moment diagram without knowing the reactions. I just need the reactions when I am going to draw the shear force diagram. But for the bending moment diagram, I don't need the reactions. How? Let's draw the bending moment diagram. The moment at A is negative 3, right? So you throw the determinate part away, right? But when you are going to draw the diagrams, you will put it with you. You are only throwing it away when you are dealing with the steps of the 3-moment equation. But you are now on the last step. You are going to draw the bending moment diagram, so you have to add it again. So the moment at D is 0. So this is A, this is B, this is B, and this is C. The moment at A is negative 3. What does negative mean? It's upwards. The moment at B, negative 4. What does negative 4 mean? What does negative mean? That it's above the datum or under the datum? Negative means above the datum. So here it's negative 4, so above. So here is 4 and here is 3. And the moment at C equals 0. Okay, so this is a determinate part, so I will join it as a straight line. How can I draw the moment for span AB and the moment for the span BC? AB, just join the beginning and the end of each span, dotted, and then here there is a uniform distributed load, so it will be a curve. And what is its value? PL squared over 8. How to draw the bending moment diagram for span BC? The same sequence. Join B and C dotted. Okay, while I'm doing this, there is not a uniform distributed load, it's just a concentrated load. You have to do like this, and then you will calculate this PL over 4, but it will be straight line. So this, instead of calculating the moment here, you can't know the moment here. Why? Because you will need the reaction to know the moment here. It's YC times 3, and you don't have the reaction, right? So instead of calculating the moment at each point, you will only calculate the moment at the beginning of the span and the end of the span. And then you will join the beginning to the end with a dotted line. And if there is a distributed load, so you will draw a curve with P square over 8. And if it's a concentrated load in the middle, it will be straight line, and the value here will be PL over 4. I think the PL over 4 and the PL square over 8, you already calculated them in the first step. So here it was 4.5, and here it was 6. They will be the same values. So now you can put the signs. And you can note the moment here as well if you need it. How I can calculate the value here. So this is 4 and this is 0. So this is 2, right? It's in the middle. 2 and then 6. So here the moment is 4. Okay? But I don't want you to calculate the moment at each point. I just need the moment at the beginning and the end of each span. Now, how can I draw the shear force diagram? In order to draw the shear force diagram, you have to calculate the reactions. You don't have any other option. You escape from this part when drawing the bending moment diagram. But for drawing the shear force diagram, which is dealing with the shear force, so you have to calculate the reaction. So now we need to learn how will I calculate the reaction first. And then after I calculate the reaction, I can draw easily the shear force diagram. There is a way here to calculate the reactions. You have to do it like me. Okay. What is the way to calculate the reactions? Split each span individually, like we did in the first part. Split each span individually, okay? So here is the span AB. And here is the span BC. What about AD? I am now on the last step, right? I'm on the last step, I'm drawing, right? So I have to take it with me. I just threw it away. Again, I am repeating and repeating. I just threw the determinant part away, the part AD, determinant part, when I was dealing with the stream moment equation method. But now I'm on the last step. I am drawing, so I can't throw it away. So each span is a simple beam. What about AD? AD from structure 1, this is called the cantilever. You know this, you have to know that the overhanging part is called a cantilever. Okay? So it's like this cantilever, fixed free. This is for the determinant part. Okay, I have here 2. And here I have 1 times 6, which is 6. And here I have 4 in the middle, right? And also, I have to put the moments here. What's the moment at A? It's 3 with the tail above. 3 with the tail above. I will put it like this. And what is the moment at B? It's -4. What does negative mean? That the tail is above. So I have a moment here which is 4 with the tail above. And the same here. It's 4 and C is 0. Okay? If I was having only the 6 in the middle, so what was the reaction here? 3 and 3, right? And what is the effect of 4 in the span here? It will give me 2 and 2, right? Because it's in the middle. But there is effect for the moments. I have to know what will be the effect of the moments. And here the 2 will go, all of it, where is support there? It doesn't have to support. So the 2 term will go here. What about the effect of the moments, the red moments? It's the same like in structure 1. The 2 moments, they are doing like a couple. They are making a couple. What is the biggest moment, the 4 or the 3? The 4 is the biggest, right? So the sigma of the moments is 1, 4 minus 3, okay? This is the bigger. In order for the span to be stable, so it's going to rotate on the direction of the 4, the biggest moment. It's going to rotate like this, right? So there have to be 2 reactions here to make the stability of the beam. So one reaction will be up and the other reaction will be down. Which one will be up and which one will be down? They have to be the other way, the other direction of the biggest moment. I have here a moment of 4 and here a moment of 3, right? So the biggest moment is clockwise, the direction of the 4. So these 2 reactions has to be anti-clockwise. They have to rotate anti-clockwise like this. Okay? So this one will be upwards and the other one will be down. What's the value? It's 4 minus 3 divided by the span, which is 6. So this one is 1 over 6 and this one 1 over 6. Okay, let's repeat it again here. Here's 4 and the other moment is 0. So the span is going to rotate in the anti-clockwise direction. So in order for the span to be stable, there has to be 2 reactions that are making a couple to return the beam to the stable part again. So this is 4 and this is 0. So this is the biggest. It's anti-clockwise. So the reaction here will be upwards and here will be downwards to make a couple, rotating in the opposite direction. So clockwise. What is the value of this one? They are equal, by the way. They are equal, making a couple, and both of them are equal. 4 minus 0 divided by the span 6. So it's 4 over 6, that is 2 over 3. And this will be the same value, 2 over 3. Now we can know the reaction at each support. Just do a summation. Just do a summation. Just do a summation. So YA is 2 upwards, 3 upwards, which is 5, and then 1 over 6 downwards. So the summation will be, so here YA is 4.83 upwards. This is the reaction at A. What about B? I have 4 reactions. All of them will be added. All of them are on the same direction. 3 and 2 is 5. 5 and 2/3 and 1 over 6. Can someone calculate it? I think it will be 5.84, something like this. I think 5.84. $5.83. And then YC will be equal only 2 forces, 2 upwards and 2 over 3 downwards. So the YC equals to 1.33 upwards. So now I have the reactions at A, B, and C. So I can draw the shear force diagram easily. Okay, let's draw the shear force diagram. So go to the original beam, original example. So Y is now 4.83, and I have here 1 times 6, which is 6, and YB equals to 5.83, and YC equals to 1.33. Just do a check for the summation of Y equals to 0. It's a stability equation, right? Equilibrium equation. 4.83 and 5.83 plus 1.33. Can someone calculate them? I think 9, 10, 11, 12. Will they be 12? They have to be 12. Why 12? Because I have 4, 6, and 2 downwards. 4 plus 6 plus 2 is 12. So the upwards reactions has to be equal to 12. This is an equilibrium equation. Sigma y equals 0. 12. So right. So I am doing right here. Okay. How can I draw the shear force diagram? Okay. Here's the datum. Here's B, A, B, C. Okay, so the shear force, I have to start from the left-hand side. I have 2 tons downwards, so I have to go down 2, and then move horizontally till I find another shear force. This is structure 1. This is structure 1 now, okay? So I have 4.83 upwards, so I am 2.83 upwards. I was at 2 downwards. I found 4.83 force upwards, so I am now at 2.83 upwards. I will go dotted. I have a uniform distributed load. There is a 6 downwards, so I am now at 3.17. And then again dotted line. And then at B I found 5.83 upwards. So I am up at 2.67. And then I will go horizontal straight line, solid line. I don't have distributed load at span BC. And then 4 downwards, so I am at 1.33. And then go and close with the 1.33. I have to correct this with a straight line. So this is the shear force line. Okay. Okay. Here I have 3 spans beam. So let's begin with the first step. So what will be the first step? Where are the supports? How many supports do I have? I have 4 supports, A, B, C, and D. Can I calculate the moment at each support? Okay, let's calculate the moment at A. Moment at A equals to 0. Moment at D equals to 0. What about the moment at B? Moment at B either from the left, I don't have the reaction YA. From the right, I don't know any reactions. So that means that the moment at B is unknown. What about the moment at C? It's also unknown, but I have here a symmetric beam. A symmetric beam. So MB equals to MC, and both of them unknown. So here again, I have only one redundant. I have only one redundant. They appear to be 2, but both of them are equal because the beam is symmetric. Okay? This is an important word. What will be the next step? Split each span. So I have here span AB, simple beam, BC, simple beam, CD, simple beam. Here I have 8 in the middle, the uniform distributed load, which is 3. 3 1 per meter, and here 8 as well. AB, BC, and CD. Can we draw the moment for each span? Yes. The moment here is PL squared over 8 and a curve. So it's 3, 8 squared divided by 8, which is 24. And here the moment is PL over 4. PL over 4, which is 8 times 8 divided by 4, which is 16. And here is the same. It's symmetric, 16. Put it on a conjugate beam, which will be simple beam as well. So the next step, calculate the areas of the moments you draw. So here is a triangle half, base 4 times height 16 divided by inertia factor, which is 1. So this will be 32. Right? Yeah. And the other triangle will be 32 as well. So what will be the reactions here? So this will be 32 and the other one will be 32. Here, can you calculate the area of the curve? Yeah, it's 2 over 3, base 8 times the height 24 divided by 1.5. Can you calculate it for me? I think it will be 85.33. Please double check. 85.33. Right? Okay. So what will be the reaction here? It's half this value, which is 42.67, and this will be 42.67. Where will you apply the three-moment equation? We apply the three-moment equation at the support that I don't know the moment. So here I can apply at B or at C. They are the same. So decide where will you apply, B or C. If you decide to apply at B, so you are done now. You just need the RB in the equation. So don't waste your time and do this part again, okay? So here, apply three-moment equation at B. So I am here now. It's very important where you are. It's very important. So I am here now at B. So what will be the equation? 2mb. Open a bracket. The span before B is 8 meters divided by the inertia factor is 1. Plus the span after B is also 8 divided by 1.5. Plus and plus. What is the support that is before B? It's A. And what is the support that is after B? It's MC, right? Put this here, 8 over 1. And this is 0, 8 over 1.5. Equals to -6 constant R at B. Okay. Moment at A equals to 0. What is MC? MC is the same equals to MB, right? And RB is the elastic reaction at B. What is the elastic reaction at B? 32 from the left-hand side and 42.67 from the right-hand side. So RB equals to 74.67. Here I can calculate MB, which is equal to MC, they are the same, is -14 meter. Can I draw now the bending moment diagram? Yes, I can now do the bending moment diagram. So A, B, C, D. A and D, 0. B and C, they are equal. Negative 14. What does negative mean? That it's above the base. Join the beginning and the end of each span with a dotted line. Okay. Here there is a concentrated load in the middle. So from the middle, make a drop with PL over 4, and this is not a distributed load, so it has to be solid line. I don't need to calculate it again. I calculated it, I think, for 16. What about this next span, BC? Join the beginning and the end of the span. And then this is a distributed load, so it will be a curve. And the value P of PL square over 8 is 24. So I think I am here at 10, right? So the noise here is 10. And the same here for the last span. So this will be the bending moment line. Let's calculate the reaction. So I will repeat what I already did for the last example. So I will repeat it again, okay? How can I calculate the reactions in order to draw the shear force diagram? To calculate the reactions, I have to split each span again, like this. The first span, the second span, and the third span. AB, and BC, and CD. For each span, put the loads. So for AB here, there was a concentrated force 8, and here distributed load 3 times 8, 24, and this is 8, right? And put the moment for each end, for each span end. For AB, here is 0. For B, it's negative 14. Negative means that the tail is up. For BC, so this is 14. The moment at B is 14, and the moment at C is also 14. And the same CD here is 14, and at D equals to 0. So calculate the reactions based only on the vertical forces. So 8 in the middle, so this will be 4, and the other side will be 4. 24 in the middle, so this will be 12, and this will be 12, and here 4 and 4. So now you calculated the reactions based only on the vertical forces. What about the moments at each end again? For span AB, the moment at A is 0 and at B is 4, so the beam or the span AB is going to rotate clockwise in the direction of the 14, right? So it will not be stable if the span is rotating. So there have to be 2 reactions in the opposite direction that are making a couple in the opposite direction of the 14. So the 14 is clockwise. So the 2 reactions that will make a couple will be anti-clockwise. So here will be upwards and here will be downwards to rotate in the opposite direction of the moment 14. What's the value? The difference of the 2 moments, which is 14 minus 0, divided by the span. The span is 8. So it will be 1.75, right? 1.75. What about here for the span BC? Here's 14, and the other side is 14 as well. So it's stable. It's not going to rotate either clockwise or anti-clockwise. They're equal. So is there an extra reactions here? No extra reactions. Even if you decided to put extra reactions, okay, what are the value of these two reactions that you are going to put? The difference of the two moments, 14 minus 14 is 0, divided by the span H of 0. So no extra reactions. What about the last span? It will be the same, like the first span. So here it will be 1.75 and there's 1.75. So YA will be equal to 4 upwards and 1.75 downwards. The summation will be 2.25 upwards. Here, YB 12 and 14 and 1.75, all of them are in the same direction upwards. So the total will be 17.75 upwards. Done. I think YC will be equal to YB and YB will be equal to YA. Now I can draw the shear force diagram. YA is 2.25, YB 17.75, YC the same as YB, YB is the same as YA. Just double check. Here is 3 times 8, 24. Just double check for the summation of y, sigma y equals 0. It is an equilibrium equation. So 17.75 and 2.25, this is 20, right? And 20, so it's 40 upwards. Downwards is 24, 8 and 8, also 40 downwards. So I am doing well, okay? Now we can draw the shear force diagram.